Let's continue with studying the angle between two vectors. As a reminder, here's the algebraic or mathematical formula if we don't have the visual. And there's always this assumption that, remember, vectors have direction and magnitude. They don't necessarily have to touch each other, but the assumption here is that if the vectors were touching, we could use this formula to determine the theta between two vectors. So here's an example. Let's suppose vector u is x component 3 and y component 4, and vector v negative 8, 6. We're not going to do visual, although with the visual and especially with some graph paper, you would make some observations rather quickly in this particular case. So if I follow through the cosine of theta formula, if you miss it from the first segment that I created, doing the dot product first has some benefits. 3 times negative 8 is negative 24, plus 4 times 6 is positive 24, and wait a second. Regardless of these two magnitudes, which are both positive numbers, the numerator is 0. This value is going to become 0 at the end. Without having to generate these two magnitudes, I can make this observation. So the dot product seems to be helpful in determining some hints about the angle between the two vectors at the very least. So if the cosine of theta is 0, well, what's theta? You recall? Well, that's right. The cosine is 0 if theta is 90 degrees. That means, however these two vectors are oriented with each other, the angle between them is 90 degrees. Now that little box there is from our days in geometry. We would have called that a right angle. Not angel, angle. We would have said that those vectors were perpendicular. But as you may have noticed, if you're reading ahead, it doesn't use either of those terms. It actually uses the term orthogonal vectors. This term is going to be the one predominantly used when we talk about vectors that would make the cosine 0, theta being 90 degrees between them. And one of the reasons for having a new word, I don't think it was meant to frustrate you, the students. I wonder sometimes about some of our things that we've built and made, if it's just trying to confuse things. But they had a legitimate reason for using a different term here. So let's just suppose that this is a vector. Let's just suppose this is a vector. Remember, vectors don't have to have a specific location. So this vector would be perpendicular to that vector in my geometry world. And this vector would be perpendicular to that vector in my geometry world. But what if I drew this vector? These words here all imply some sort of connectedness, things that are touching. Vectors don't have location, and so the word orthogonal it describes that if they were touching, they'd be perpendicular. You'd have an angle of 90 degrees, but they may not be touching. Now, remember this is a flat piece of paper. This is 2 dimensions. What if my vector was above the paper? they're definitely never going to intersect each other, and they're never going to touch. So they're not perpendicular in that sense. So the word orthogonal means if they would be touching, you would see that they make a right angle. Oh, I should just point out too, I could put a vector sticking straight up here, and there's a right angle there, and there's a right angle there, and there's a right angle there. You can't see all of this. In the classroom with my arms and my body standing vertically, I can imitate orthogonal much more profoundly, but it looks a little bit silly when I do it. Let's check out another example. So we've got two vectors here. Notice I did not put hats on my vectors. I hat, j hat, k hat. They are optional in my classroom, but you better check with your physics professor. They may not be optional in their classroom. Our book does not use the hat symbol. It uses a bold font. So, notice I'm missing a number. I want you to find that missing number such that U and V are orthogonal. Let's make them perpendicular if they were touching in 3 dimensions. We want the cosine of theta to be 0. And we just saw that in order for the cosine of theta to be 0, we would start by doing the calculation of the dot product over their two magnitudes, and we would want this to be 0. So 2 times 7 is 14. 5 times the component V2, and then 3 times 4 is 12. I want 14 plus 5 multiplied by V2 plus 12. I want that to be 0. All right, some little algebra. 5V2 equals, that's right, negative 26. V2 is equal to negative 26 divided by 5. This is the value that would have to go here if we wanted these two vectors to be perpendicular if they started touching from the same origin. Our new term we're using is orthogonal. Orthogonal. All right. Until next time, when we'll look at another application that uses dot product.